So in this video, I wanted to determine whether the given vector u, so I'll call this u, is in the span of S, where S are these three sets of vectors. I know they're matrices, but in linear algebra, the general term for an element is a vector. So how would you do this? Well, basically what you're trying to check for, so you're checking whether u belongs to the span of S, right? That's what you're looking for. This is what you're looking for. So this is like a question mark. That's my goal. So how do you know if a vector belongs to the if a vector belongs to the span of a set? Well, you know that a vector belongs to the span of a set. So you know that a vector belongs to the span of a set, Remember that the span of a set is the set of all linear combinations of vectors in that set. So you know that a vector belongs to the span of a set if it can be expressed as a linear combination of the vectors in that set. So because the span of a set is the set of all linear combinations in that set, you check if a vector is in the span of a set by seeing whether it can be expressed as the linear combination of vectors in that set. So for simplicity and so I don't have to write the matrix over and over again, I'll call this vector v1, this vector v2, and this vector v3. So basically what I'm looking for is I'm trying to see whether u can be written as c1 v1 plus c2 v2 plus c3 v3. Right, so basically what I'm looking for is I'm looking for c1, c2, c3. I'm trying to see if there's a solution for c1, c2, c3. So now I'm going to have to write the whole matrix down. So it was 1, 2, minus 3, 4 equals c1, 1, 0, minus 1, 0 plus c2, 0, 1, 0, 1 plus c3, 1, 1, 0, 0. Right, so now what I have to do is I have to create a system of linear equations with the above equation, so with this. Okay, so what I do is I take each matrix entry, and I create a linear equation with it. So my first equation is going to be 1. So the 1, 1 entry, so I'm looking at this entry here, is equal to c1 plus c3. Then my second entry, so my 1, 2 entry is going to be 2 is equal to 0 plus c2 plus c3. My third entry, so 2, 1, is going to be minus 3 is equal to minus c1, and that's it, so minus c1. And then my last entry is going to be 4 is equal to c2, and that's also it. So already I'm going to skip the, well, I'm not going to skip it, I'm not going to put this in a matrix form, because I think if I just use if I just use these two equations, then I can solve for C3 in my other two equations. So let me just label these 1, 2, 3, 4, and this is my system of equations. This is my system of equations. Okay, so already I know that C1 is going to be equal to 3. I just multiply both sides by -1, and that C2 is equal to 4, right? So I'm going to solve for C3 in 1 and in 2. In 2 and in 1. So you're probably thinking, well, I can just solve for C3 in 2, get an answer, and then say, okay, well, I'm done. Well, no, because you want to make sure that the other equation, so in this case, equation 1, corresponds or gives the same answer as in equation 2 to see if the system is consistent. It's basically the same thing as getting 0, 0, 0, and then a constant. It's the same idea. It's just that I'm trying to see if I get a contradiction in that kind of sense. So from 2, what I get is I get 2 is equal to 4 plus C3. So C3 is equal to -2. And then from 1, I get 1 is equal to 3 plus C3. So C3 is -2. So it looks like both my answers match up, and I get so my solution will be, let's see, C1 is equal to 3, C2 is equal to 4, and C3 is -2. So I do get a solution. So this means that my vector, which was initially the matrix, it was this matrix, that was my vector u, 1, 2, -3, 4, that my vector u can be expressed as a linear combination of my vectors. And my vectors, remember, v1, v2, v3 were 1, 0, -1, 0, 0, 1, 0, 1, and 1, 1, 0, 0. So my vector u can be expressed as a linear combination of v1, v2, v3. Hence, so that means that hence u belongs to span of S. So u is in the set of S because it can be expressed as a linear combination of the vectors in S.